Hi, welcome back again. So now we are going to DC to DC converter, and the first one we're going to talk about is the boost converter. Imagine you have a 3.7 volts battery, your lithium battery, and you need 5 volts to charge your phone. The boost converter's work is to step up the voltage. Step up the voltage maybe from 5 volts to 12 volts, from 9 volts to 15 volts, in thereabouts. When you need to step with DC voltage in a not so far range, you can use boost converter. Alright, let's go ahead and see how a boost converter works. So we go to our simulation. Let's create a new circuit, a blank circuit. So for that, we're going to need our 555 timer as an oscillator. So I'm just going to come here and add a simple one of these circuits here. Alright, so this already connected. Don't forget you can use the formula of this, the formula that we used in the previous video on how to get the oscillation frequency of an astable multivibrator using a 555 timer, to know what is the frequency of this oscillation here. So we are going to let's move this one a little to the side. So now this is an oscillator oscillating at a particular frequency. So a boost converter needs an inductor and a switching component like a transistor, a feed effect transistor. So what I'm going to do now is I will need my resistor, of course. Let's first add the resistor, 2 resistors. Then I need my transistor. I'm still going to use the BJT, bipolar junction transistor here. Okay, so let's connect these points. Okay, that's correct. This other point goes to ground. Alright, that's also correct. This also goes to ground. Okay, that's good. Now let's add boost converting circuits. The part that actually gets to convert the voltage from the 5 volts to a higher voltage. So a boost converter circuit contains an inductor. Yes, you're probably hearing about inductor for the first time. An inductor is also a passive electronics component. Involves a diode in this manner, then a capacitor in this manner. Yes, do you see this now? Now the arrangement between here, and this transistor, all these four makes a boost converter. Do you understand? Now let's connect this place to 5 volts also. Sorry about that. Let's make it full screen again. So we know that the supply voltage reaching here, the supply voltage here is 5 volts right from here. But what will be the voltage here? Let's add a scope, view in new scope there. to see what the voltage here will be. Don't forget the value of this resistor should be something high. Let's make it like 100k. This is to ensure that this transistor fully switches off when it switches off. So I have one bad connection from here, and is this red spot. So I'm going to delete it, and redraw it. So let's draw it in this manner. Let this one first connect to this, then this one to connect to this. Okay, that's good. Okay, let's run this simulation to see what will be the output voltage. Now you see 6 volts, 11 volts, 17 volts, 19 volts, 22, 26 volts. You see that 27 volts here now, 28 volts is the output voltage. But what if you need is what you need is just maybe 12 volts, right? The voltage is controlled by the duty cycle of this oscillator. The fuller the duty cycle, the higher the duty cycle, the duty cycle, the value of this inductor, and the switching frequency. The duty cycle, the value of this inductor, and the switching frequency. Actually, in real life, if you are going to get a 1 Henry inductor, is going to be a very large inductor. So I'm just going to, let's step this down. Let's use like 10 millihenries, 10 millihenry. And we are going to see 10 millihenry inductor. And you see the voltage still rising. Stop simulation, reset, let's restart the simulation. You see the voltage kept rising to 30, 44, 48, and all that, right? But can you generate 220 volt AC with this? Yes, you can, but it's not efficient. I will show you another method. This will be our final project for this particular course. Okay, I will show you that in a separate video. Now, to cap this voltage to a level, we are going to find a way to regulate what the output voltage will be, right? We have to find a way to regulate it. So there are a few ways to do that. You can use the control terminal of the 555 to do that. So let's start. I will need a potentiometer. Then I will need a resistor. Now, if I can connect this side directly to the power supply. Okay, that's a false connection. Stop simulation. I'm going to first delete this, then connect like this, and like this. Okay, that's good. Set this like 10k. Okay, start simulation. Oh, of course, there needs to be a load resistor here. Let's add a load resistor. Aha, you see now we are getting something meaningful. You see how the voltage has dropped vertically. Let's just reset it. Yes, now we have some meaningful value. So at the output, you have 7 volts, 7.3, 7 point something. Let's delete this. Let's delete this line and see what will happen. Yeah, this is more reasonable now. The output voltage is 9 volts instead of the 140 volts that we were seeing before. That was simply because there was no load resistor there, and in real life you will not likely get up to that even if you forgot to add your load resistor. But voltage can be outrageously high. It can be between like 40 or 30 volts, right? So now that we have a load resistor, the voltage is within control as it's a bit. So without this part added to it, we found out that the voltage is reaching around, maybe from here we see 9.96 volts, 5.9, 5 point something mass scale. You see the voltage in this manner. If I calculate the frequency from here, this should be giving me around 500 hertz. Now, most switching regulators, they use frequencies up to above the sound frequency. The reason for that is simple, so that you will not be hearing the noise produced by that oscillation audibly. So if you've ever had some chargers make like a high frequency pitching sound, like they didn't take cognizance into the frequency of oscillation they used in their design. So let's we just change the value of this capacitance to like 30 nanofarad or 0.03 and click OK. That's 30. Oh, no, that's not what I mean. It was 3 microfarad before, 0.03 microfarad. And click OK. Now you discover that when I increase the frequency, this pulses smoothing out better. So the higher the frequency, the more cleaner the output you will get from your buck or your boost converter, from your boost converter. Okay, so since we've done that, you see the output voltage is around 5.286 volts. The input voltage and the maximum voltage is this 5.286 volts. 5.286 volts. All right, not bad, right? And you know the reason for that actually is because this part, there's still a current flowing from this part to ground. So let's remove this part. That's what we have. Let me reset it again. You see now, you see the output voltage, I'm getting 11 volts, 10 volts, thereabouts, 10 volt output, 11 volt output, and it's fluctuating. 10.9 volts now, 10.98 volts. So let's connect this point back and connect this point to. So now we can use this potentiometer here to control the output voltage. Output voltage here. How it hits, I will explain. The voltage at the output will still fluctuate depending on the load. Fluctuate largely depending on how much load you have there. So presently the voltage on the output is 5.449. That's around 5.59 volts. So let's say we want a 9 volts output from this 5 volt supply. I will just change the value of the resistor. As I increase it, you already see the waveform rising. I already have 6.4 volts. Increase it, you see 6.9 volts. Increase it, Now I have 7.7 volts. Now I have 9.2, 9.4, 9.4 thereabouts. So at this state, we have a regulated output voltage, simply because we took the power supply, part of the power supply, and fed it into the control terminal of the 555 timer. Albeit this regulation will change with changing value of load, changing amount of load. Let's practicalize that. So presently we have 9.355 volts, right? Let's change this to 1.5k and see what will happen. Let's see the voltage. Let it settle. You see the voltage has changed to 9.385 from 9.355. If the load increase by reducing the resistance to like let's 800 ohms, what will happen? The voltage will also drop because it means more load. You see now the voltage is dropping 9.3, 9.34, 9.341. You see that. Now if the let's say you now have like the load increased to like 300 ohms, you see the drop in voltage, you are getting like 9.277. Actually this is not very bad actually, but this is because it's simulation. In real life it's going to be way more affected than that. And to cope that's why we don't connect this point to the power supply. We use it as a form of feedback. That is, you connect this point to the output voltage. You connect it straight to the output voltage. So it's like taking part of the output voltage and feeding it back to the inputs, so that you can control what the output is, not minding the amount of load. Do you get that? So let's set it back. Now we have like 16 volts on out, 16.5 volts. Let's set it back to 9 volts and now adjust. Let me make this load 1 back. This is 16.5 volts thereabouts. Let's make this load 1k and see if we still remain on 16.5 volts. I have 17.2 volts, right? So let's make it, I want to make it 9 volts. $10.6 volts, 10.4 volts, 10.1 volts, and it's still dropping actually. 10.1 volts. So I have my 9.3 volts now. 8.9 volts. Let's adjust it a little. 9, good. This is 9.09 now. I have 9.09 volts on the output, fluctuating a little bit. If you want to reduce the amount of fluctuation, you can increase the value of the capacitance. Albeit it also affects the output voltage too. But you can always adjust back. You see now it's smoother. But the voltage has dropped to 8.7 volts. So I can adjust back the value of my potentiometer to compensate for that. 8.8, 9.015 volts. Now for little changes in load, let's see if this will still remain at 9.0 thereabouts. If the load reduced to 900 ohms, what happens? You see, it's still stable, still 9.015. If the load reduced to 800 ohms, what happens? Still 9.015. Do you see now? If the load reduces or increases rather to 700 ohms, still 9.015. If the load increases to 600 volts, 600 ohms, we still have 9.015. If the load increases to 500 ohms, we still have 9.01, now 9.014. You see, very small amount of change. That's like 1 millivolt change for that amount of increase in load. Let's see at what point it's going to change significantly. Let's say it's 300 ohms. Now we have 9.00 volts. That's 15 millivolts change. You see this now. So this is better regulated. This is well-regulated power supply. And this is more efficient because it's actually a switching power supply. The amount of energy wasted in most cases for switching power supply, depending on the circuit you use, is around 10%. Unlike linear regulators that they can use up to 50% wasted as it. Do you understand? So this is a boost converter. A boost converter increases the voltage from a lower voltage to a higher voltage. Now, in the same way, we are going to use this same circuit to simulate a buck converter. This same circuit as it is now. Let's stop the simulation. Let's stop the simulation, and I'm going to use this same circuit here, but arranged in a separate way. So I will delete this. This one will no longer be here. This one will no longer be here. Let me not delete it entirely. Let me just delete the connection points. We'll move this downward. We'll rotate it. Flip. Is it flip now? No, it's not flip. I need to rotate it. Good. Rotate it. I will disconnect these points. Let's delete this point too. We are going to reconnect it. Now the diode comes here. The diode comes here. This point goes straight to your power supply. This point connects to your transistor. In this fashion, and this point connects to your output. Good. Now this arrangement is a buck switching regulator, buck converter. What will this do? This will reduce the voltage in an efficient way. So I'm going to set this at 15 volts. But I want the output voltage now to be 5 volts. So I'm going to connect this one here in this manner. Good. We are going to delete this. and this. Still the same circuit. Let's leave this as, let's start with 1K here. 1K. So here we have a buck converter. A buck converter, what does it do? It steps down the voltage. Unlike the boost converter that steps up the voltage, a buck converter steps down the voltage. Alright, now that we have this, let's simulate the circuit. Start simulation. Do you see the output voltage is dropping, 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 dropping. The input voltage is 15 volts. The output voltage is 6.8 volts. Let's make it, we want to step it down to 5 volts, right? 5 volts. Now let's say you have a laptop power pack. You want to create a charger to charge your phone from your laptop power pack, or carry on this project with extreme portion anyway. You can build these circuits and adjust the value of this resistor until you have 5 volts at the output. So let's begin to adjust. Begin to adjust, dropping it down. .8, 5.7, 5.6, dropping. Still dropping. It's going to be faster than this in real life. Hope you know it's going to be way faster than this in real life. Okay, we've over adjusted it. .346 volts. Let's reduce it a little bit more. It's too much. Okay, 5.347. That's okay. Okay, so we have this at the output voltage. Let's see if we change the value of the resistor, or if we increase it, will it change the output voltage? If we increase it to like 2 kilo ohms, will it change the output voltage? Not really. 5.4 volts. If we reduced it to like 500 ohms, what's the output voltage? 5.29 volts. You see now. So this is a buck regulator, right? Okay. The same circuit, we just change the orientation of what is done here. So with this, we have successfully created a DC to DC converter, both in the boost and in the buck. Boost means that it will step up the voltage. Buck means that it will step down the voltage. Switching regulators are actually a high efficiency regulators, and you won't have to go through the hassle of actually building one yourself, right? You can just buy a complete module online, switching regulator module online. The LM2596 can be configured both in buck or boost, already pre-made, so you may not need to buy. but to build one with yourself, I mean. But for experimental purpose, you may want to create your own power bank using lithium batteries, 3.7 volt lithium batteries. If you want to do that, kindly comment in the comment section of this video, and I will guide you through what you should do to get that done. All right, thank you. Please don't forget to like this video, subscribe to this channel, and enable the notification button so that you can always receive our latest video when we publish them. Thank you for watching.